Our next presenter is Dr. Ahmed Zayyad. He is an environmental engineering expert from Environmental Engineering Group. Please welcome to the podium. Jamie, you have
بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد النبي الأمي الكريم. Dear gentlemen, distinguished guests, as it's mentioned in the Quran, everything life is created from water. وَجَعَلْنَا مِنَ الْمَاءِ كُلَّ شَيْءٍ حَيٍّ. Actually, we are here like to address such topic not related to the industrial process of the district cooling or HVAC, but it represents the research and development, scientific, practical examples can assist the designers or the developers of such system, which we are calling the computational fluid dynamics. It's recently science since last 15 years, and it is used in all the industries and OEMs who are producing chillers, pumps, or any mechanical parts, and also the hydraulic components. So how we can analysis and how we can help the designers to take a right decision for enhancement and optimization of the system as a total solution. As we have seen previously yesterday, Mr. Marwan Khoury from Dar al-Handasa, he presented all his district cooling design parameters, and finally he addressed to CFD, and someone asked me, what is the role of CFD in such topic like district cooling? So our agenda or our topics of contents, we will give the methodology and the practical example about the methodology, which representing the finite element, or what's called in terminology discretization, and also we'll describe the numerical hydraulic modeling, how we can do it, and finally we'll have some reference list or a case study can touch and tackle the HVAC systems and also the water and wastewater industrial process equipment. First of all, what is the CFD? What is the computational fluid dynamics? CFD as a branch from fluid mechanics, and every mechanical engineer working in thermodynamics or hydraulic engineer working in water hydraulics, he should to know about the CFD, because it is application of the numerical analysis, and all of us, we have been studied undergradually the numerical analysis, such mathematical numerical models which can represent some differential equations to be implemented for design of any chillers, or you can design any equipment, or you can design any component touch flow. What is the definition of flow? The flow can be identified by stream, pressure, velocity. Even it is gas or water or any type of other fluid. So the ongoing research have invented some software applications can help the input parameters of any design system, and he will give you the prediction of the results in terms of velocity pattern or pressure pattern or streamlines or whatever you need, instead of investing too much cost in what's called physical model. To make a model or scaling model, you can do it very simple, low cost, by using of supercomputers which exceeds more than the processor of 2 gigahertz. Our methodology as an industrial application or all OEMs, not the supplier, the original equipment manufacturer, they have their own R&D laboratory, research and development laboratory. You will do first step is pre-processing. And pre-processing is to use the graphical user interface to simulate the geometry of any model. And this data subsequently we can name under the simulation. How to draw the boundary conditions for heat exchanger, evaporator, or pump, or piping, or chiller, whatever the system is the pre-processing. And also we are calling something related to the physical boundary. What is the surrounding boundary of your component, and what is the effect of the subsidiary tools, instrumentation implemented in your physical boundary conditions. Also we'll create a mesh or a grid representing small discrete finite points which can lead to accuracy for predictions of the results. Because all of us, we are using such formal equations, but we are giving velocity, pressure at certain point. But within this point, with discretization methods, you can create millions of points within the finite element analysis. Second, we can make also for example, heat transfer. We have the enthalpy as a terminology from the thermodynamics. Also, how to measure the total energy. And everyone is talking in such steam event for the energy. And energy is a term can be represented and it can be reduced without the theories and without the practical application. You can predict before implementation of your system, is it economical or optimized energy-wise or not. Second thing, also the problem for transit analysis. Transit analysis, we have seen it in like water hammering. We have seen one presentation yesterday, or transit analysis, how can the water oscillation, how can you represent this, and you can protect your system from surge, or you can protect your system from the transit flow. Well, the second step, as the first step we mentioned, we have to develop the physical geometry and to implement the boundary geometrical surrounding conditions. The second one is to make the flow analysis and what type of computational physics you will use, and in order to predict the performance in such way can not deviate from the actual performance in future after execution or after implementation of your component. As we know very well that we will develop whatever the flow, steady flow or unsteady flow, and turbulent flow. And we know very well Reynolds number. It is representing the time of the flow. What is flow is laminar, whether the flow also is turbulent, and we can estimate the case which you like to study and to feed the numerical equations by such input. Finally, a post-processor. As we described on the beginning, the pre-processor. Finally, we'll describe the post-processor, which how can we see our results physically on the monitor or on report or in output reports with visualization. Like we like to see the model itself in three-dimensional to ensure that our design will be optimum design. Let us focus in one of the most common practice everyone can use easily with such software applications available in the market is discretization method, which is the finite element method. What type of equations can use for such simulation? Navier, Stokes, and all equations like Bernoulli equation, energy equation, the term of kinetic energy V squared over twice G, or the term of pressure, thermopotential energy, how you can elevate this bulk over a certain datum. and the terms of this equations and continuity equation, so you can predict the actual flow performance within the method of implementation. As we know very well, this is proportional also to the gradient of velocity, that if you have also a hydraulic profile and you have a kinetic energy converted from a potential energy, so you have the velocity gradient, how can be stepped. And finally, you will have to control the geometric volume, which in three-dimensional or in space. So you can see which you cannot see in actual performance on the site after implementation. Also, as it was mentioned, energy conservation. So you can reduce the energy, you can make a good economic consumption of energy of your system via such simulation with the discretization or discrete the finite element, or what's called FDM. Another method also, it is subsequently to discretization method, which is finite element and finite difference, the difference between each parameters. And also, this will lead to what is mentioned yesterday in the design parameter of the district cooling about the delta T, which can be optimized the round of the pumps of the electrical part, electromechanical part. Is it within centigrade Celsius 6 or 8 or 10 or 12? How can you select the best alternative match with your proper total solution system? And then we'll go with hydraulics. It means instead of using gas or air, we'll use water. What such component of hydraulic can be implemented in your system? And solving the complex flow problems, we can use it by such applications available in the market like Fluent, like three-dimensional flow, CFX, and here in Middle East or in Saudi Arabia, there are a lot of Asians selling such software. And then we'll go give you as a case study for practical example for anyone how you can analyze. Everyone, maybe someone asking me, this superstitious method, how you will implement such simulation and methodology and using this complicated scenarios. It is very easy for any simple simulation, because if we see here, the capabilities is if this flow is laminar, turbulent, steady, unsteady, single, multi-phase, energy conservation, mass momentum, or rheology. Rheology is the matter deformation, or even you can predict the plumes, the feeders in the water, or other industrial applications, or water reservoirs, or also any hydraulic component have a mechanical parts. Let us focus on our topic of this team event for district cooling. What is the role of CFD to be implemented in district cooling? District cooling, I take a case study or practical example for the cooling tower. How you can simulate a cooling tower and create what's called prestigious model. How you can create a prestigious model via CFD? It's very easy. If you will see here, this is the schematic drawing illustration for any mechanical engineer. He can see what is the heat transfer and what is the cooling fan, what is the evaporator, what is the cooling tower technology. It is here how you can simulate this. Very easy to simulate it. To make a study for any cooling, you like to study the temperature. What is the primary and secondary circuits? What is the air or liquid flow? What is the power level? What is the pump capacity? What is the fan capacity? With all those items, you can create your model. Very simple also in the total surrounding building, the circumferential of this system, and also have a sufficient accuracy how to build the building with a certain intensive boundary simulation program. And also what is your interest for these predictions, and also what is the target in terms of thermal climate exchange, climate impacts. As we have seen here, many people talking about the climate change and what is the impact of the temperature on the surrounding ecosystem. Also, finally, some people illustrated in their presentation the effective of using variable frequency drive and how you can use this CFD drive to minimize and to optimize the energy and what actual load, how you can optimize your equipment. So all these parameters is the input of your prestigious model. Finally, is to have to be handled such experience. You can take templates or you can take previous examples and just you will make the load calculations by edit or something, and you will have the output, and you can feed the input of the output of such HVAC system to the model of the cooling tower. As we see here, this is the model with geometrical boundary, and what is the geometrical boundary within the connection of all total solution cooling system. And also, if you see here, this is the mesh which I described before, the finite element mesh, and the nodes, the grid nodes. So if you see your system here, this is the output of the air, and here also this is the heat exchanger and how many rows and columns and the recirculation. So if you will see here, it's very simple to create those nodes by geometrical physical boundary conditions, because the computer, supercomputer, will divide the grid into small parts. And what type of system? Like the common system for closed with cooling, for example, as I have taken this example for simulation, and how it's matched or not with the prototype, the actual physical, and how can you assist your also the pressure pattern with the velocity, because the velocity of the air will enhance the energy itself. Here also this system, as it was mentioned before, what is the impact for ozone or ozone depletion potential as mentioned in the first presentation. So such prediction of this system can lead to environmental friendly outputs, and the emissions will be reduced. What type of system you can use also in evaporator condenser? That's the shape, if you see here, and the inlet air, heat exchange coil, spreader props, the drift eliminators, and outlet. And you can see here, this is the mesh, and here you will see here the pressure distribution in Pascal, and here you will see the velocity distribution in meter per second. And if you will see, for example, that we can reach up to here 14 meters per second velocity for this red, and the differentiation in color pattern represents the figures of the velocity profile within the, if you see here, this is the vertical positions, and here you have the also temperature. So the second example I like to also present, it is related to serve the total solution of the HVAC, which is the water process, the equipment, the industry of such WW, what's called water and wastewater. How can you simulate? Because the flow pattern of any hydraulic system, it can enhance the deposition or sedimentation or accumulation of grit of any pump with well, or also change in the mass, and also can tackle the connections of such intakes or a series of pumps in parallel, how the second pump can go within the system, and how it can affect the influence suction of the previous pump, and what if the total discharge will be accumulated from two pumps, is it 90 or 95%? All of this you can simulate by using such technique of CFD. If you will see some illustrated example, three-dimensional of very common example, any mechanical engineer using every day, like sump or like recirculation pumps or like piping. You will see here for pump sump, for example, 4 pumps, 3, 1 plus standby, and if you will see here the streamlines. This streamlines, some of the engineers like to predict the flow streams and how can affect with the velocity. Or if you have 3 pumps and 1 in standby, how the intake. And this will give you the real dimensions of the intake or of the bay or the inlet channel influence raw sewage or water intake in desalination plants, because most of us just you will fix such dimensions and ensure the capacity of the wood well according to stop and on of the pump and the volume added, and then you will say, okay, I need this volume like this as per motor cycle on and off per hour like this, and then you will give very big wick well capacity, and the civil work will be high costly and also other subsidiary costs. Thank you. Here also we can continue one of the most common practical example, the streamlines of the previous example or regarding the pump pre-sphere rotation. The pump itself, it is you have vortex surrounding the pump, suction of the pump can enter what's called entrapped air, or it will also the pump shape, how can the pump shape will be fixed, and also as you know the bell mouse shape or the pump resting phase, how can affect the design of the geometrical of the pump well itself. And if you see here, this is the length and the cross sum, and also it will give you the in velocity means the magnitudes surrounding the pump, which cannot exceed, for example, 2 meters per second. This is also T-junction. Very simple T-junction, you can also simulate the flow within the T-junction. Also, if you will use RO system, you have a pressure vessel, you have a membrane, what is spiral wound already with spermatic, for example, installed within the pressure vessel. What is the simulation within the pore size and how will affect the flux within the simulation of the sheet itself. Also, if you have a valve, one presentation was talking about how we reduce the surge via controlling the valve by VFD or actuator. You can here simulate this very easy. Also for the chemical engineers, one from Veolia asked me how CFD can be implemented in such chemical reactions by means of this liquid density or velocity drop and vectors within the salt and fresh water. Also, if you have some diffusion, this diffusion, how you can predict the geometrical surrounding streamlines within the diffuser itself, whatever the diffuser in water tank or in the sea or whatever the application. The conclusion, from one expert as a CFD specialist, we like to conclude, what is the aim to have a CFD in your designing tool in engineering section? The reliable hydraulic structure, how we can predict also the flow pattern, and also if you have the behavior of such total solution with the total system, and also have you some phenomena regarding how to implement the such system components together to work together to final achieve goal of the energy consumption, and how to implement also such model for experimental work, because as you know very well, as I mentioned before, the cost of experimental model or bench scale model or what's called physical model, it is highly costly than using numerical model, because numerical modeling is only computer software. And finally, the last slide, to be tight in time, the hydraulic optimization, which this is the aim of this illustrations, to give you such idea how to lead a significant saving in energy, and also, as I said, in civil works, in the example of the wet well and geometrical design of the pumping station, the construction, which any mechanical engineer, he will maybe I didn't like to say neglect, to take into account the whitwell cost. He will fix the volume, but it is very sure for any structural and civil to take care into consideration what is the construction cost, the capex cost for such implementation of pumping station. And we've done this example here in Khomra South, one of the biggest plants of pumping station, around 12 cubic meter per second. It means one pump can deliver discharge of Q 1 meter per second, 1 cubic meter per second within 40 meter head. Also, per each pump, you can see the motor sizing around 500 kilowatt. So if you will use 12 pumps, what is the energy consumption in megawatt? So the energy-wise should be taken into consideration before start the design, because CFD will lead for a proper and optimized design solution. Finally, I'd like to say something. It is expected that within this year or done already, maybe last year, with software applicators, that the computational performance will be more accurate. And this will lead to such a new numerical. Instead, I described the previous 10 years used, which is called finite element method. The new recently generation of such model rely on large eddy simulation, or what's called direct numerical solution. And direct numerical simulation, you can use it in turbulent flow, much easy, and will become computationally affordable to the near future. And thank you for your attention. Thank you, Chair.
And now I want to welcome Mr. Ziad Sabiti, the General Manager of Sales and Marketing of Future Pipes, for his presentation. Please welcome him to the floor.